So just some reactions involving carboxylic acid derivatives. So first, I'm going to go over anhydride cleavage. So this is when you react a anhydride with a molecule, and that causes the anhydride to split into two. So it's a nucleophilic acyl substitution reaction that splits the anhydride into two molecules. So like I said before, you can interconvert the acid, carboxylic acid and its derivatives. So you can change an anhydride into an amide. When you react an anhydride with ammonia or an amine, so what happens is the anhydride reacts as an electrophile, and the ammonia or the amine as the nucleophile, and this splits the anhydride into two. So you form one amide and one carboxylic acid from an anhydride group when that happens. So this is similar to, it's like the opposite reaction of forming an anhydride. So instead of reacting two groups to form anhydride, you react a group of the anhydride in order to form two other functional groups. Similarly, ester formation, when you react an anhydride with an alcohol group, the anhydride reacts to the electrophile, and the nucleophile is the alcohol. This forms an ester group and a carboxylic acid. So the side of the anhydride that reacts with the alcohol turns into an ester, and then the other side forms a carboxylic acid. And same thing, you can reform that carboxylic acid that formed the anhydride when you react the anhydride with a water molecule. So you reform the two anhydrides that were used in order to create that anhydride. So this is the general mechanism for anhydride cleavage. So in this reaction, you react an anhydride with an alcohol group. So when that alcohol group attacks that carbonyl carbon, it forces the electrons from the double bond onto that carbonyl oxygen, and the oxygen in the middle between the two carbonyls, it takes a proton from that alcohol group, and as a result, since you have the negative oxygen from the carbonyl and the positive oxygen from the middle of the molecule, in order to break it off, what happens is the negative charged oxygen will resonate the electron down to reform that double bond, and it breaks off the other molecule when the electrons from the carbonyl carbon and the oxygen go on to the oxygen in the middle of the group. So what happens is the alcohol, the carbonyl that was attacked by the alcohol group will form an ester, and then the other side forms this carboxylic acid. So this is anhydride cleavage. When you do cut an anhydride and reform the carboxylic acid, and then whatever the nucleophile was, will determine what the other side of the anhydride forms when it's cleaved. Next, I'm going to go into transesterification. So this is when you change the type of ester the molecule is. So this is when an alcohol acts as a nucleophile and displaces the esterifying group on the ester. So this is when a new alcohol attacks that ester in order to kick off the alcohol originally on that ester in order to form a new ester. So the ester transform into a different ester. as you can see, it's a similar mechanism. So the red alcohol, so this new alcohol group will attack the carbonyl carbon, resonate the electrons from lone pair onto the oxygen, and this forms this tetrahedral intermediate in the middle, and you can reform the carbonyl because alcohols are good leaving groups. So what happens is the electrons from that negatively charged oxygen will resonate down to reform that double bond. And as a result, it kicks off this red OR group. It kicks off this blue OR group. So the original alcohol group attached to the ester. And when it kicks it off, it forms this new ester with the red OR group instead. So this is when transesterification is when you convert an ester into a different ester by using a different alcohol group. So this is transesterification. And next I'm going to go into amide hydrolysis. So this is when you cut an amide group into the original carboxylic acid and ammonia or amine group. So the amide, it can be hydrolyzed under acidic or basic conditions, and this is done via nucleophilic substitution. So what happens is the carbonyl oxygen will accept. So in acidic conditions, the carbonyl oxygen will accept a proton from the solvent. This causes the molecule to have a positive charge, and this allows alcohol to attack via a nucleophilic substitution. So when the water group attacks the molecule, it forms the tetrahedral intermediate that you see on the top right. And what happens is the amide the amine or the ammonia group that was attached to the carbonyl carbon, it will accept a proton from that water group that was added. As a result, it protonates the amine or ammonia group and makes it a good leaving group. So one of the OH groups can resonate down to form a double bond in order to kick off that ammonia or amine group. So this reforms the carbonyl and it kicks off the amine or an ammonia group. So this is the opposite of amide formation. So amide hydrolysis, you reform the original carboxylic acid and the ammonia or amine group that you use to form that amide in the first place. So this is the reverse of an amide formation. I'll give everyone this question. The following tetrahedral intermediate reforms a carboxylic acid. What will be its leaving group? The answer is choice C. So as you can see in this molecule, the only good leaving group is this molecule this group right here. OHs aren't good leaving groups unless they're protonated, and this alkyl group is not a good leaving group. So the only good leaving group is this OCH3 right here, and choice A is the trick answer because OCH3 would have a negative charge, and usually so when molecules have when it leaves with a positive or negative charge, that's not favorable, so it would have to be usually a neutral leaving group. So when it leaves, this OCH3 will pick up a proton in order to form HOCH3. So that would be choice C.